Okay, we've got 10 science experiments to film. In 3, in 2, are you ready? In 1, and go!
Right, we've got 2 minutes 30 to do 10 experiments. Let's go! First experiment. There's dry ice in there, the pressure's going to build up. It's going to go like a rocket.
No, and that's the pressure's building.
It's on.
Okay, pressure's building up.
Peers and colleagues all en route now to your first conference. Got your data and your poster, but where's your confidence? Arrive early, posters up securely for your session. You neatly piled all your handouts, you're sure you got enough. They're on display full of anxiety. You'll be fine, boy, pitched up right next to me. Yeah, it's your first day at the conference, yeah.
We'll have an answer for you.
Life of Cells, recording in 1, 2, 3.
They say they love us. We are precious. We matter for quality results. But you gotta wonder. They say that without us being happy and healthy, that they would have nothing, but they put us through all this and expect us to perform.
Can I get a sample? I'd really like a sample, yeah. What's the sex of testicular DNA? Can you walk with me every step of the way, yeah?
I'm here to talk to you about the two worlds of cell isolation. In science, we're constantly faced with change. New discoveries, new facts, new paradigms. So here's the thing. The most commonly used product for cell isolation, referred to as microbeads, are actually only 50 nanometers. Therefore, they're not microsized at all. They're nano-sized, and they're not beads at all. In fact, they are random and irregular in shape. Confusing, I know. So let's just call them nano-sized particles, or nanoparticles. They kind of look like cornflakes. And since these nano-sized particles are largely comprised of iron and polysaccharides, you could say that they resemble sugar-coated cornflakes. So let's compare this to the micro-sized planet, where larger magnetic spheres, or beads, are used.
I got millions of assays like a buffet table. Choose any application cause you know that I'm able to shape discovery like a hammer and anvil. I'm the cream of the crop, you're a watered down sample like Usain Bolt. You know I'm ready to run. Design and promise milk curves ain't no fun. I'm specific, prolific, reproduce for you. I'm a real hard player, but I'm sensitive too. Man, I get your point, but don't agree with this thesis. You have to synthesize different probes when you got different sequences. I bind the DNA, even when more is created. So sorry, homie, look like Tech-Man's complicated. And why you gotta push me on my choice of chemistry? Results are all that matter, this look pretty good to me. My mind is prime for primers and I use my frontal lobe, while you're waxing lackadaisical, dependent on the probe.
In the early 80s, we were asking, what if we could end the laborious and time-consuming methods used to identify, clone, and purify DNA? Then a DNA polymerase was discovered. Derived from a naturally occurring hot spring inhabiting microbe, Thermus aquaticus, these microbes could actually replicate their DNA close to the boiling point of water. We use these polymerases to amplify DNA, further advancing our research, moving forward, evolving, adapting, experimenting. Thermal cyclers automated this process of heating and cooling, and then Mastermix was invented as an optimized cocktail for PCR.
Ambion cells to CT kits provide a simple and rapid method for preparing cell lysates.
And the fact that I can combine my day job, which is to develop technologies, with my love of discovery of new biology, I'm the luckiest scientist there is. MicroRNAs as a field really got started very slowly back in the 90s.
Our cells produce large numbers of different small RNAs. They're called microRNAs, and they regulate about half of all the genes expressed in our cells.
If you want to kind of envision what we're dealing with here, I guess maybe you should see Manhattan as one big organism with all these different cells. Every building is a cell, and then how do all these buildings, how do they communicate with each other? And that's through these these small objects that are running around through these streets. When you look here from the 28th floor, you see all these taxis driving around, but they're so small you can hardly see them. And I guess when you go really downstairs, perhaps when you take a big microscope, and all of a sudden you see that a taxi is much more complex than just a yellow dot. Actually, there's a lot of things going on in there.
In this video, you will see how Dynabeads coupled with protein A or protein G allow for immunoprecipitation in just 3 simple steps.
Because of the history of protein isolation and the move from large-scale protein purification to immunoprecipitation, people tend to believe that this capacity actually is crucial, when in fact capacity isn't always a good thing. The fact is that you want to balance the capacity, yield, specificity, and cost.
The application changed, and at first they were trying to use the same tool. For antibody purification, Cephros is a great tool. For immunoprecipitation, it turned out to be not so well suited. You only have a certain amount of antibody, and you want to specifically bind a protein. When you look at it this way, the pores are bad news because they actually trap the antibodies and unwanted proteins inside and between the porous resin.
So I'm doing gradient PCR, trying to optimize the annealing, and I need to find the precise temperature. But instead of setting a range, I wish I could set specific temperatures at the same time. And then I get to imagining a day with gradients and no precision. What would that be like? It'd be like making my breakfast, and yet no matter how hard I try, I just can't get the perfect toast. It'd be like heading off for a much needed coffee at my favourite coffee shop, and I'm not able to order the right size. So with a coffee so ridiculously big it needs a straw, I head for my car. I get in, take off, but I have only a vague idea how fast I'm going.
We see a lot of variation between different systems. Some systems we see high product quality but low titers. Other systems we see high titers but low product quality. And we oftentimes trying to look for a system that does both.
When developing the XB293 expression system, we wanted to be able to generate very high levels of protein in a very rapid period of time, as well as make sure that those proteins were of high quality.
All the greats have sat here in this chair, and they knew what I know, that it is just a question of the right part. Because when we choose, it's a star performance every time. So we have to get it right, as at the end of the day, we get permanently typecast. You better be sure, because there is no turning back. These guys knew exactly what they were doing, and I could do any one of those parts. Of course, I'm the man.
Ah, the name's Shell. Stem Shell.
Yeah, baby, yeah!
No, I am your father.
See? It's easy.